Section 16.4 is about one of the most important theorem in multivariable calculus, one out of the three. So the other two are Stokes theorem and divergence theorem. This is the first one out of the three most important theorems in multivariable calculus. It is known as Green's theorem. Green is due to Mr. George Green, which was a British scientist, mathematician, and physicist. Brilliant guy. Basically, what he came up with was a relationship with what? A relationship between a line integral around the simple closed curve C and a double integral over the plane region R. In other words, he came up with a relationship between the line integral, what? Around the simple closed curve to what? A double integral over the region, not the curve anymore. So basically, this is how the formal definition or Green's theorem go. Let C be a positively oriented. First of all, what's positively oriented? That means the curve, the direction of the curve is what? Counterclockwise. So positively oriented means the curve is, the direction of the curve is what? Counterclockwise. Piecewise smooth, that means there are no sharp edges anywhere. Simply closed, the curve doesn't intersect itself in the plane, and let R be the region bounded by the what? Curve C. If P and Q have continuous partial derivatives on an open region that contains R, so here is the Green's theorem, which says the line integral over the vector field, remember in this case, a vector field is what? Pxy, qxy. So this is the same as this line integral f dot dr, except it's in differential form, right? So px dx plus q what? P of xy times dx, q of xy dy is exactly the same as f dot dr, but this is called differential form of this line integral. So it's over a vector field. You just see the components. So whatever is attached to the what? Dx is the x component of the vector field. Whatever is attached to the dy is the y component of the vector field. So Mr. Green discovered that this guy is exactly the same as double integral, but the integrand has to be what? Partial of the y component with respect to x minus partial of the what? X component of the vector field with respect to y. Note the order. This guy has to be taken, the partial derivative of this has to be taken with respect to x, whereas the partial derivative of the x component has to be taken with respect to y. And you got to subtract these guys and notice the order because the order matters. So this partial has to go first, followed by this partial. So please do not change the order. So now, suppose we like to evaluate this line integral by two methods, first by the direct way, and then by Green's method. And here is the line integral. So notice just by inspection, you know the vector field has its x component as x squared y squared, and the y component is xy, just by inspection. Whatever is attached to the dx is the x component of the vector field. Whatever is attached to the dy is the y component of the vector field. But the C, the curve C, consists of three C's. First, you go from 0 to 0, 0 to 1, 1 via this equation, which is y is equal to x squared. Then you go from 1, 1 to 0, 1 via this equation, which is y is equal to 1. and then you go 0 to 1 to back to 0, 0, and the equation of this line, C3, is just what? X is equal to 0. So in order to do the line integral, that means the direct method, I have to parameterize each of these what curves one at a time. The first one is what? Is a parabola. So if x is t, y is t squared, and t goes from 0 to 1. Notice the order matters. So keep track of the order now, yes? It goes from 0 to 1 because we decided x is t, but x goes from 0 to 1, so does t. So dx is dt, and dy is 2t dt. So hold on to this. Let's go over C2. C2, y is 1, but x varies. So x is t, but notice t goes from what? From 1 to 0. 1 to 0. Follow the order now. T goes from 1 to 0 because t is the same as x. X goes from 1 to 0, so does t. Okay, then this line on the y-axis, x is 0, but y is t, but check this out. Y goes from 1 to 0, correct? Because y is t, y goes from 1 to 0, so does t goes from 1 to 0. Once again, check the direction. In each case, you have to find dx and dy. In this case, dx is dt, but dy is 0. In this case, dx is 0 because x is 0, but dy is dt. So now, go this line integral 3 times. Once for what? C1, then for what? C2, and then for C3. So this would be for C1, this would be for C2, this would be for C3. So you got to repeat this line integral 3 times for each curve, right? But the what? The last one is 0 because when you get to dx part and x's are 0, so you get 0 for C3. But for C1 and C2, you have to follow the direction. Remember, like for C1, x is t, y is t squared, dx is t, dt, dy is 2 t dt, and this is basically what you got. For C2, x is t, y is 1, dx is dt, dy is 0. So portion of the what? A line integral for C2 is 0. So all you get left is these two integrals. Evaluate those guys, right? Factor out the dt, evaluate this, then evaluate this, add up the answers, and lo and behold, the answer is 22 over 105, correct? Now, Mr. Green says, you know what? Because you have met all the conditions, which are, you have a simple closed, what? You have a closed curve, which is positively oriented, which is like what? It goes counterclockwise, is piecewise smooth, okay? So it contains a region, so that way you can have an area. Otherwise, if this region was open, then the Green's theorem does not apply. Green's theorem applies to a closed region, yes? And on top of it, the curve has to be, the boundary of the region has to be what? Positively oriented, meaning it has to go counterclockwise. If it goes clockwise, then you have to multiply the integral by negative. Okay, it's piecewise smooth. So looks to me all the conditions are satisfied. We are good to go to apply the what? Green's theorem, which says that line integral can be converted to double integral provided the integrand is difference of these two partials, which the order very much matters. Very much matters. Okay, so this would be like partial of what? Q with respect to x. This would be partial of p with respect to y, because your p was x squared plus y squared, your q was xy. And what? You going from what? So this is dy dx, which is dA, and you're going from, let's say, the parabola to the horizontal line, and x goes from 0 to 1. Okay? When you evaluate this, lo and behold, you get the same answer. So that's the beauty of what? Green's theorem. So instead of doing what? 3-line integral, going over the what? The sides, all the curves which the region is contained. If you satisfy the conditions of the Green's theorem, you can do the whole problem in one shot, which is one double integral gets you to the same answer as line integral got you to the same answer, but by performing the line integral 3 times over each of these c's one at a time. Do you see it? But then there is a pitfall for green theorem. First of all, if the region is not closed, everything is out the door. The second is about the vector field. Let's say you have a vector field like this, and let's say C1 goes from what? 1, 0, right, to what? Negative 1, 0, and C2 goes from what? 1, 0 to negative 1, 0. So in other words, C is the union of two C's. Problem is, the region R contains 0, 0, at which your what? Vector field is undefined. Do you see it? If you replace x's and y's in the denominator with 0, these fractions blow up. So the moral of the story is the Green's theorem doesn't apply. Be careful. So Green's theorem doesn't apply rain or shine. It has to satisfy certain conditions. Okay, one of which happens to be what? The vector field has to be defined in every point, what? In region R. In this case, 0, 0 is part of your region, but the function is undefined. Okay, at 0, 0. Therefore, Green's theorem doesn't apply. The other scenario is what if the what? What if the, let's say, the region was open? What if I go like this, but I don't close this up? So now the Green's theorem is out the door once again. Do you see it? One of the beauties of Green's theorem, besides evaluating the line integral, it also finds the areas of regions, specifically irregular areas, like, let's say like this. Let's say this is a lake, and you like to find the area of the lake. Okay, so this is kind of like an irregular shape, but how do you find the area of an irregular shape? Well, the Green's theorem will help you to do that as well. How? Remember, to find the area using what? Double integral, the integrand had to be equal to 1. Do you see it? Do you remember? So in Green's theorem, what did we have? We had double integral, partial of q with respect to x minus what? Partial of p with respect to y. So if somehow this difference is equal to 1, then this guy will find the area of region R. So the question is, under which condition this difference of two partials is equal to 1? Well, it turns out the possible answers are, if P is 0, Q is X, in other words, the vector field is 0x, then this partial will be 1. How? The partial of q with respect to x is 1. The partial of what? P with respect to y is 0, so you get 1. Do you see it? So if P is 0, Q is x, this difference becomes 1, and if that difference is 1, then you find in the area of the region. The other scenario is if P is negative y, Q is 0. The third scenario is if P is negative 1/2 of y and Q is what? Is, let's say, positive 1/2 of x. In that case, also the difference of these two partials is 1, and therefore this line integral, if this difference is 1, finds the area of the region R. So if you summarize these three scenarios, the area can be found by using what? Line integral, either by this line integral, or this line integral, or this line integral. So there are three ways to use the line integral to find the area of a closed region. Okay, let's do a very simple example from first semester calculus. How about finding the area of the region enclosed by the what? Parabola, and x equals 2 and the y-axis, you know, this region right here. Okay, all you have to do is pick one of these, not all three, just pick one. I chose this one to find the area. Notice if you were going to do it by calculus way, you would go, okay, the area is antiderivative, x squared, what, dx, right? X goes from 0 to 2, you get 8/3. But if you apply the Green's theorem, you can also find the same area. I know this is easy, but remember, the idea is to find the areas of irregular regions, like, you know, a lake, some place, you know, some region which it's not perfect shape, like, you know, perfect geometric shape, like parabola or ellipse. It's not any of that, you know. This kind of shape does not follow any geometric shape, so it's very irregular. So therefore, those are the occasions we use what? Line integral, using what? Consequence of the Green's theorem to find the area. How do you do this? Well, instead of what? Integrating over region R, we integrate what? Over the boundaries of R. In other words, I'm going to take this integral and repeat that 3 times for each of the boundaries of the R, C1, C2, and C3. So therefore, the area is line integral over C1 plus line integral over C2 plus line integral over C3. Okay, so what you have to do is parameterize each of these curves, like C1x is t, y is what? 0, y goes from 0 to 2. C2, this guy, x is 2, right? Y is t, t goes from 0 to 4. Okay, because that's the y. C3, x is t, y is t squared, but check this out. T goes from 2 to 0. You're going from 2 to 0 because that's the value of the x. So when you do these line integrals, lo and behold, what? You add up the 3 answers, you get the same answer as you had before. But keep in mind, this is not designed to find the what? A perfect geometric shape area. This is mostly designed to find the areas of what? Of irregular shapes. In real life, what happened is there is a device which is called planimeter, and that's basically what they do in real life. So in practical application, the device is called planimeter. This is how it looks like. So this is what? A fixed arm of the planimeter. So this is fixed. Then you have this elbow here. Then it has this arm here with a pen. So what you do, this is the end of the planimeter, which traces the shape. So what you do, you take this pen and go around the curve, correct? Okay. And lo and behold, there is a digital device here, and that reads the area, and that's called planimeter, and the architects use this to find the area of a irregular shape, which the concept behind it is Green's theorem. When you find the area of an irregular shape using what? Line integral, which is the consequence of the Green's theorem. So if you just Google this, you will see planimeter, the device itself, as opposed to cartoon. So Google this and see how planimeter looks like um, in real life. Thank you.